So today's lesson is about writing a rate law from a multi-step mechanism. And I just happen to have one sitting right here. This would be called a multi-step mechanism. Now don't forget that a mechanism is just simply chemistry code for an explanation of how the chemistry actually happens. And if it happens in multiple steps, that simply means that in order to get from the reactants to the products, it's going to take more than one chemical process to get you from point A to point B. Now, when you're considering a multi-step mechanism, we are going to have a series of chemical equations, and it can be difficult to know which one of those equations that you would want to write a rate law from. Now, just as a reminder, each one of these steps is what we would call an elementary step. In other words, in any one of these steps, the chemistry happens exactly as it's written. So an NO2 plus one other NO2, they quite literally have to collide to make these two products. So again, in an elementary step, the chemistry happens exactly as it's written. So to try and do a multi-step mechanism, we would have a series of elementary steps all added up to make this overall picture. Another key component of a multi-step mechanism is that they often include a type of chemical called an intermediate. Now, an intermediate is a chemical that is first made and then immediately consumed in the next step. So when you're looking at identifying an intermediate, what you're going to look for is a product in step 1 that then becomes a reactant in step 2. So it only exists in that very short amount of time between step 1 and step 2. And if I was identifying one for this particular chemical reaction, I think I would pinpoint NO3. So notice how NO3 is first made, but then it is consumed in step 2. So NO3 is actually the definition of an intermediate, a chemical that is first made and then used up in the following step. One nice thing to note is that when you're writing a rate law from a multi-step mechanism, you never include these inside of the rate law. Now, we may need to include them temporarily to get from point A to point B, but the final finished rate law will never include an intermediate. Now let's focus on writing the rate law directly from this multiple step mechanism. Honestly, as far as chemical reactions are concerned, even if you have a process that happens in multiple steps, your overall reaction is only going to be as fast as the slowest step. What we call this step is the rate determining step. So although there are other steps that may in fact have their own little rate law, the rate of those particular steps are so fast that they don't limit the overall chemical process. This step, noted as the slow step, will be so much slower than the remaining that you can actually set the entire rate law just simply according to the slow step. Now, what's beautiful is that the easiest type to write a rate law for overall is if the slow step is the first step. Now, the reason for that is because we're going to write the rate law always from these reactants. And generally speaking, for the first step, the only thing that you're going to have in here is reactants. If you move on to step 2 or step 3, the likelihood is that one of the materials that you write the rate law from would include an intermediate. And don't forget that we do not write intermediates inside of a rate law. So for this particular reaction, if the slow step is the first step, I would simply define the rate law as rate equals K. And in this case, it would be times NO2 times NO2. And you could simplify this to K equals NO2 squared. That would be completely fine. So again, writing the rate law directly from the elementary step, the easiest kind of rate is when the slow step, the rate determining step, the step that determines the whole rate of the whole reaction is the first step. Generally, there's only actual reactants in that step. You can go ahead and just write it clean out because there would not include any intermediates. Now, the last thing that you can do with a multi-step mechanism, this does not actually show the overall chemical equation for this process. It doesn't show the net equation. So what we would want to do is to simplify and then write the overall equation. Now, the only thing that we really need to do is to cross off like terms. So if there's anything that's the same from the reactant side to the product side, we can actually cancel those items out, and then we would simply rewrite what we have left over. So the first thing that we already identified as an intermediate, something that is first made and then consumed, we would want to cross that item off. If there's anything else that you notice that's the same between the reactant and the product side, you'd want to cancel that out as well. I notice that I have an extra NO2 from both the reactant and the product side. Now, this is not an intermediate because it is not first made and then consumed. It is first consumed and then remade. That's actually the definition of a catalyst. It's something that's first used and then remade. So it emerges on the other side completely unchanged. That would be essentially, again, the definition of a catalyst. Okay, I don't see anything else that I need to cancel out, so then let's rewrite what we have left over, net. So the reactants stay the reactants. So I would have an NO2 left over and a CO left over. And then on the product side, it looks like I have an NO and a CO2. So this is the overall equation for the reaction. I think it might be a good idea if we see a couple more example problems. So let's erase this slide and let's actually see a couple more. So let's check out this problem. This is actually a pretty common style of problem where they actually give you the overall equation for the chemical reaction that you're studying, and then through experimentation, you actually develop a rate law. In this case, rate equals K times NO2 times F2. And then from that, you can kind of see that this rate law, there's no way that it could have been written directly from this chemical equation. If it had been written directly from this chemical equation, we would be seeing instead rate equals K times NO2 squared F2. But that's not what we're getting experimentally. So there must be some other explanation chemically for why we're seeing this particular rate law. That means that as far as the explanation, there must be a different mechanism for how this reaction actually takes place. And that generally indicates a multi-step mechanism when we have this disconnect between the chemical equation and the rate law. That usually, again, means there's a multi-step mechanism. So oftentimes you're provided with a mechanism and you're simply asked, is this mechanism consistent with the observed rate law? In other words, could you write this exact rate law from this mechanism? Well, let's find out. Let's write the rate law directly from this mechanism. Now again, what you want to do from a multi-step mechanism is write it directly from the slow step. This is the rate determining step. And in this case, rate would equal K times NO2 times F2. Now what's lovely again is that my slow step is my first step, which means both of these materials are both reactants in the overall chemical process. I don't have any intermediates or anything. I don't have to do anything fancy. So is this rate law that we see written from this mechanism then consistent with the observed rate law? Well, if it matches, yes, it is consistent. And that's essentially the end of that problem. You get to simply say, yes, it's consistent, or no, it's not consistent. Does it match? Yes. Does it not match? No. I think it might be a good idea now if we try a problem where the slow step is not necessarily the first step. Let's take a look at this particular chemical example here. Now we have a multiple step mechanism and we're going to need to write the rate law from it. Now notice that in this case, the slow step is not the first step. The slow step is the second step. And unfortunately, it is going to include an intermediate. C is first made and then is consumed. That's the definition of an intermediate. And that's not going to be allowed in my final rate law. But for right now, I have no choice. I must write the rate law from the slow step. So for right now, my rate is going to equal K times my concentration of C times my concentration of E. But again, I need to get rid of this intermediate. Not allowed to have it in there. So the process that you're going to end up doing here is the process of substitution. Notice that the previous step is called a fast equilibrium step. Now in equilibrium, and this is actually a little preview of the chapter to come, the rate forward equals the rate of the reverse. So in other words, the rate of A plus B going in this direction is exactly the same as C plus D in this direction. That allows you to write a very specific expression for rate. So if rate forward equals rate reverse, let's write the forward rate law. I'm just going to leave out the K for right now, just because they're going to end up canceling out anyway. So it would normally be rate forward be K times the concentration of A times the concentration of B. And let's write the rate reverse, so it would be in the other direction, pretending that these products are now reactants. That's going to equal the concentration of C times the concentration of D. Well, okay. Now it's C that I want to replace from my original rate law. So I'm actually going to solve this expression for my intermediate. Solve it for that intermediate product. Okay, so I'm just going to divide this over. I'm going to divide D over. So I'm going to end up with A times B divided by D equals C. And what I have now is the ability to substitute C out for other materials that are not intermediates. I'm allowed to have all of those reactants and all of those ingredients on the inside of my rate law because they're not intermediates. So using our original expression, let's substitute this out for C. So I'm just going to write it into its place. So what I'm left with overall is that rate equals K. And now instead of writing C, I'm going to write all of this malarkey times the concentration of A times the concentration of B divided by the concentration of D. And then What's left over is this E stuff here, so let's also put in E. You have just now successfully written a rate law for a chemical process where the slow step is not the first step. We still have to write the rate law directly from the slow step, but it did include an intermediate. So what I did is I went up to the next step, which is labeled as fast equilibrium. Equilibrium means that the rate forward equals the rate reverse. So I wrote this little expression. I'm just kind of eliminated the K's, where the rate law for the forward reaction equals the rate law for the reverse reaction, and I solved for my intermediate. This allowed me an expression that I could substitute into my overall equation that did not have an intermediate in it anymore. The last thing that you could do with this particular problem would then be to write the overall equation, the chemical equation for this reaction. This is not the rate law. Remember that you're going to need to eliminate anything that you see that's exactly the same from the reactant to the product side. C was an intermediate. It was first made and then consumed. So I would want to eliminate that. I don't see any other repeats, so now I can simply drag and drop down. A plus B, and I think we also have E plus E, makes D plus F, would be the overall equation. So I think it might be a good idea if you see just maybe one more problem that's very similar to this, something else that has substitution, maybe like a real chemical example. And here we go. So again, here's my overall chemical equation and my observed rate law. The question that would go along with this particular problem is, if this is the mechanism down below, can this mechanism explain this observed rate law? The only way to find out is if we actually write the rate law from this mechanism. Now again, what I notice is that my first step, or my rate determining step, is not my first step. I still need to write the rate law directly from the slow step. So let's do that. Rate equals K times the concentration of NOBr2 times NO. Now what I want to do is just examine to make sure I didn't have any intermediates in there. And unfortunately I do. NRBr2 is made in this first step and then consumed in the second step. That's the definition of an intermediate. So I am not allowed to have NOBr2 on the inside of my rate law. I'll need to substitute that out. So let's work up one extra step. This is my fast equilibrium step. This is where the rate forward equals the rate reverse. So rate forward equals rate reverse. What I do know, and again, I'm eliminating the K's. I would normally write K times NO times BR. I'm just skipping the K part. That means that I know that the concentration of NO times the concentration of BR2 will equal the concentration of NOBr2. Now I don't even have to do any algebra or anything. Now I have an expression that I can use to substitute out the NOBr2. So what I'm going to do is I'm going to take this and replace that on the inside of my original equation. So now I can rewrite instead rate equals K, and instead of NOBr2, don't want that because it's an intermediate. Now I'm going to write this instead. NO times Br2, and then I can finish with the NO that was left over. And yes, you can simplify that one more time. Rate equals K times NO squared times Br2. So is this rate law consistent with what's observed? Well, I guess yes, it is. So I have rate equals K times NO squared times BR, and this should have a little 2 behind it. That's just a small typo. That's my fault. So yes, this is actually consistent. How about one more problem where we're actually writing a rate law from a slow step that's not the first step? Let's try this little problem out. So this actually is a 3-step process where we have 3 chemical equations all combining down to make one overall equation. Now, if I was to write the rate law from this, again, you always write it from the slow step. That would be this bottom step. So I know that rate is going to equal K times my concentration of E. Nice, simple rate law. Unfortunately, E is an intermediate. E is first made in this previous step and then consumed. So I am not allowed to have E in that equation at all. So I'm going to go up to the next step, or to the previous step, and notice it's labeled as being fast equilibrium. And that means that my rate forward equals my rate reverse. So I can write that beautiful little expression where I just eliminate the K's, but it would be C times D would equal E. And that's wonderful. I don't have to do any algebra or anything to just solve for my intermediate. I already have that done. So now I can substitute for E this expression instead. So I'm going to plug that in. So now I'm left with rate equals K, and instead of E, I'm going to write this now, C times D. Well, let's check to see if we're done. So I have C in here. Uh-oh, looks like C also is an intermediate. It is first made and then consumed. That's the definition of an intermediate as well. Let's double check on D. D looks like it's only a reactant, so I think I'm safe with having D in there, but I do still need to substitute out C. So let's get that started. We go up to the previous step from that. That's also labeled as being fast equilibrium. So again, I know that my rate forward equals my rate reverse. I'm just going to eliminate the K's, but then I know that my concentration of A equals my concentration of B times my concentration of C. And it's C that I'm trying to get rid of, so I want to solve this expression for C. What that means is that A divided by B equals C. And now I have an expression that I can actually substitute back into here yet again. This was a double substitution problem. So because I know C also equals this, let's plug that in instead of having the C. And let's write what's left over. Rate equals K, and instead of C, I'm going to write this, A divided by B, and what's left is also D. Now, none of those are intermediates, so this would be my final rate law from this multi-step mechanism. This was a doozy because it had a double substitution in it, but I thought this was worthy of of showing you that you can get your way through this one. The only other thing to do would be to write the overall equation from this particular problem. Okay, so again, when I'm trying to write the overall rate law, the overall chemical equation from this mechanism, I want to try and cross off like terms. So E was an intermediate. It was first made and then consumed. Let's get rid of it. And also C was first made and then consumed. So we want to eliminate that as well. I don't see any other duplicates, so let's write what we have left over. A plus D would be on the reactant side. We'll make B plus F. And this is my overall equation.